Okay, so since we're going to deal with diffraction today, this is just a quick intro. So we have an incoming wavefront here in a circular aperture. So the portion of light that goes through the circular aperture, at this point, every single point within the aperture diameter becomes a new point source and starts projecting its own wavefront. So this causes a diffraction pattern due to the constructive and destructive interference, and we get an airy disk.
So we calculated the Fresnel number using this equation. For a given Fresnel number, we could solve for L, and using Z1 equal to the focal length, we're using a meter-long focal length. We could solve for Z2 for an NF of +1. We found that this was 436.4 millimeters. So the Fresnel number is defined as the number of half-wave zones over the aperture. For a Fresnel number of 1, we expected this pattern with a dark spot in the middle. So for the setup, we have the laser, the spatial filter, the collimating lens. We checked for collimation with the shear plate, the mirror at 45 degrees, the test lens, an aperture, and the microscope. So moving the microscope changes the number of Fresnel zones, as we see here. So the point spread function of an optical system is described as the impulse response to a point source. And so if we have a point source for the object, we convolve it with the point spread function, and we get the point spread function as the output. The line spread function is the impulse response for a line object. So the optical transfer function can be thought of as either the autocorrelation of the scale pupil function or the Fourier transform of the point spread function. The modulus of the optical transfer function gives us the MTF. The MTF is defined by the image contrast divided by the object contrast, and where the contrast or the modulation is defined in terms of the maximum and minimum image brightness. Since it is a Fourier transform of the point spread function, it will be a function of spatial frequency, and so we will have a cutoff frequency given by this equation. Essentially, the MTF is, and so the MTF basically gives us information on how well an optical system can resolve spatial information.
Here we have a Bessel sync pattern. This is the curvature you get in a diffraction limited system, or a point spread function of that system. Here we have the airy disk right here. This is the smallest resolution you can get in one of these systems. 2 Fresnel zones corresponding to 1 wave of defocus, and we could use the -2 Fresnel zone and the 2 Fresnel zone to find the best focus by averaging out those 2 spots. To profile this beam, we moved a slit over the spot A, which is the radius of the aperture, 7.7 millimeters diameter, and then we have the wavelength and the distance itself, which is given by this equation. We can use the imaging equation to solve for L, Z2 and Z1. The slit width itself that we used was a lambda F number. So given the cutoff frequency, we could find this width.
So as we scan the slit across the spot, we end up with a knife edge trace, the derivative of which is the line spread function.
We took our measurements for the best focus with the 83 micron slit width and the 12 line per millimeter cutoff frequency, and ran the data through the MATLAB program provided, and we got back these plots for the line spread function, which shows a sharp peak, and we also see the MTF plot here to the right, which is the magnitude of the Fourier transform of the LSF. The dotted red line is the diffraction limit, and the solid green is our measure value. So we can see in the plot we are really close to the diffraction limit. Okay, for one wave of defocus, which belongs to the Fresnel number 2, we can see this little dip in there, which is expected as the drawing. We can see there's a dark spot in the middle. And then if we take a look at the MTF, we see that the solid red line is more spread than previously. With the data collected for the -1 wave of defocus, we should be getting the same thing that we saw last time for 1 wave of defocus, but we're not. So this is probably due because of stray light measurements, which threw off our data, and we ended up with this incorrect plots. So, I mean, we should be expecting a dip as well in this plot, but we did not get it.